Okay, so let's look at theorem number 6. Theorem number 6 is talking about finding points of inflection. And you're like, what does that mean, points of inflection? Okay, so here's the best example I can give you right now. Picture a third-degree graph looking something like this, right? If you notice, there's a point here where this kind of like starts concaving up, and then there's a point where it concaves down, right? There's a portion. Well, when it flips from concaving up to concaving down, that point is known as the point of inflection. There is a point where it changes, it switches from concaving up to concaving down, or vice versa. With me? And so this theorem helps us to find that point where the switch happens. You can't see it with the naked eye because it's extremely subtle. Because it's like, okay, it's a nice smooth curve, and that's true. But there is a point where it actually does change, though we can't see it with our naked eye. With me? All right, so this theorem helps us to find it. So it says, if f has a point of inflection, it must occur at a value x sub 0. It's an x value, don't worry about the subscript. A value x sub 0 that's actually in the domain of f, where the second derivative, when you plug in that x sub 0 to the second derivative, it equals 0. Or that plugging in of x sub 0 to the second derivative does not exist. Now, there are a few things happening. Some things occur with the first derivative, some things occur with the second derivative. And so I want to kind of start laying that out here so you can kind of see what the first derivative does for us and what the second derivative does for us, okay? So, let's talk about the first derivative. When I have the first derivative, right? What does the first derivative help me find? It helps me find critical values. So, I can find critical values with the first derivative. How do I find those critical values? When I take the first derivative and I set it equal to 0, that helps me find a critical value, doesn't it? What else does the first derivative help me find? Good. It also helps me find where functions are increasing or decreasing, correct? Okay, and based on that, I can find relatives, mins, and maxes. Agreed? All right. Now, the second derivative. New information. The second derivative now tells me, based upon this theorem, I can find points of inflection by taking my second derivative and setting it equal to 0. If I take the first derivative and set it equal to 0, I find critical values. If I take the second derivative and set it equal to 0, I find points of inflection. With me? Okay. The first derivative helps me find increasing and decreasing. The second derivative helps me find concavity. Concave up or concave down. With me? Now, increasing and decreasing and concavity will help me find relative mins and relative maxes. Okay, both of them will do that. That's not a problem. But I need to understand what each derivative does. The first derivative, its main object or goal is to find critical values and help me determine where functions are increasing and decreasing. The second derivative's major objections are help me find points of inflection and concavity, up or down. Cool? Okay, got an example coming up next. So let's look at this example. It says sketch the graph, list the coordinates of extrema and inflection, if any. State where the function is increasing, decreasing, and concavity. I know I threw the if any in there, but you know you always have to have that in the back of your mind. If any points of inflection, if any extrema, right? Okay, eventually I may have to take the second derivative because of inflection and concavity, but I can't take the second derivative until I take the first derivative. So let's start there. So now let me ask you something. When you find the first derivative, what can you find from it? Good, you can find critical values. So, first, let's find the first derivative, which will lead to critical values, right? Okay, so our first derivative looks like negative 3x squared plus 6x, yes? And so how do I find the criticals? Set this equal to 0, and then we get to solve, right? Whoops, that's a 6x. And I'm seeing an x squared, which means I am going to factor out a negative 3x, which will leave me x minus 2. Do you agree? Okay. And then I get to set each of these equal to 0, which means one of my criticals is 0, and my other one is a 2. So here are my critical values, and 0 and a 2. Got it. Now what? Good. Find the y's that go with them. You know, just like we were doing before, nothing's changed. So second, right, we're going to find the y's, or known as f of x in this case. So f of x, right? Well, what's my first x? 0. So let's just put 0 in there. So f of 0. Plug a 0 into here. Yeah, we get negative 2. So I have one of my points is 0, negative 2. Cool? All right. So then we plug in the other critical, which was 2, into this function. So let's be careful. I'm going to work it out at the same time. 2 to the third is 8. So I have a negative 8. What's 2 squared? 4. 3 times 4? 12. Minus 2. So that looks like 4 minus 2, which is 2. So it looks like my other point is 2, 2. So here are my 2 points. Cool. Okay, got it. And now what do I have to determine? Yeah, I've got to determine if those are relative extremas. Now I have a couple of different options to do that, don't I? I can still use my first derivative and plug these x's in and see where it's increasing and decreasing on either side of those critical values, can't I? Or I can use my second derivative and find the second derivative and find the concavity, which will also tell me relative mins or max, won't it? Now here's the deal. I am going to go with the second derivative to determine the relative mins or max, which in actuality will also help me find increasing and decreasing. Like how? Watch. So third, I'm going to use the second derivative test. And this is going to help me not only find extrema, it's also going to help me find concavity and increasing and decreasing. So just hang in there a second. So, by the way, just watch and then rewind the tape and rewind the video and then write your notes down. But just watch for a second. Here's my first derivative. When I find the second derivative, it's a negative 6x plus 6. Is that correct? Okay. And I am going to take each critical value, the 0, I'm going to use that one first. When I plug it in, I get 6, which is greater than 0, right? It's a positive number, which means, which way does this concave, since I'm talking a second derivative? That means this concaves up, which means we have a relative min at y equals negative 2, and it occurs at x equaling 0. Correct? Okay. But I also had a second critical value of x equals 2, didn't I? So I'm going to plug that in. And when I plug that in, it looks like I end up with a negative 6, which is less than 0. Correct? Which means this concaves which direction? Yeah, this concaves down, which means we have a relative max at y equals 2, and it occurs at x equaling 2. Do you agree? Okay. Now, that second derivative test helped me to find the concavity. It helped me determine a relative max and min in this case. And you're like, but wait, didn't you say it helped me find increasing and decreasing? It actually does. And here's how it's going to help me find where this increases and decreases. So just watch. I am going to draw myself the x-axis. So we have negative infinity to positive infinity. I had two critical values. What were they? 0 and 2. Right? From the work we did, we determined that at x equaling 0, right, this concaved up. And let me be a little bit more specific, if you don't mind. That would be wonderful. At x equals 0, it concaved up. The y value was negative 2. So technically at 0, negative 2, this is concaving up, isn't it? And over here, at x equaling 2, but the y was a 2. So what was this point? This point was 0, negative 2. This point is 2, 2. At this point, it concaved down, didn't it? Right? Okay. Here's how you can determine your increase and decrease. From negative infinity to 0, wouldn't this graph have to be coming down this direction to connect with this part of the concave? It would, wouldn't it? Which means from negative infinity to 0, that part of the graph would have to decrease, wouldn't it? Do you agree? Okay. Now, on this section, wouldn't this part here have to increase to connect with this part? Right? This has to increase anyway. So let me get rid of this for a moment. I jumped ahead of myself. Wouldn't this part have to increase here? Yes. From 0 to 2, it would have to increase, wouldn't it? If I look at this part over here, for this concavity, wouldn't it have to increase to connect with this concavity? So from 0 to 2 again, increase, same interval. And on this part, from 2 to infinity, wouldn't this part have to decrease? So the decrease is also happening at 2 to infinity. Your critical values cut your x-axis into three pieces. Negative infinity to 0, 0 to 2, and 2 to infinity. And if you take a look, wouldn't negative infinity to 0, wouldn't this part have to decrease to connect with this concavity? From 0 to 2, wouldn't it have to increase on both of these? They would have to increase, wouldn't they, to connect with this concavity? And then from 2 to infinity, wouldn't they have to decrease on this end in order to continue that concavity? Okay, good. Are you guys with me? That's how doing this second derivative test not only helps me find the concavities, visually it actually helps me find where the increase and decrease has to occur. With me? Okay. Now, there was one other thing that they asked me to find, which was a point of inflection. Now remember, that was the new piece of information. The point of inflection is found by taking the second derivative. Do you agree? So, when I look at the second derivative, which we already found over here, and I'm going to give myself a new title because this is the fourth step, right? This is the point of inflection. I take my point of inflection and I set it equal to 0, don't I? Pardon me, I take my second derivative and set it equal to 0, right? And then I get to solve, and I get x equals 1, right? Okay. But I got to find the y value that goes with it, don't I? So here we have to find the y that goes with this, or the f of x, right? Okay, which means I'm going to find f of 1. So I plug it back into the original. When you're finding the y, you always plug it back into the original. So I've got negative 1 plus 3 minus 2, which will give me what? Which will give me 0. So my point of inflection is 1, 0. Are you with me? Okay. Now, I'm going to pause this here for a second. Why? Because I need more board space. Why? Because I actually need to sketch the graph of this thing. And it's going to take me a little bit to erase the board. So stay tuned for the conclusion of this problem. So here's the information we had found. We found the critical values at x equaling 0 and 2. We found the points that went with them. We determined at x equals 0, it concaved up, which means we had a relative min at y equaled negative 2. At x equaled 2, we found that it concaved down, and so we have a relative max at y equals 2. We found it decreased from negative infinity to 0 and from 2 to infinity. We found it increased at 0 and 2. And we found a point of inflection at 1, 0. Okay, so we found a lot of information. So here's the deal. Let me start putting things on our graph. We have the points 0 and negative 2 and 2, 2. Right? We actually have the point of inflection at 1, 0. And point of inflection, POI. Got it? And we determined from negative infinity to 0, it was decreasing. And it was also decreasing from 2 to infinity. And it increased between 0 and 2. Correct? All right, so this is what I've got this graph looking like. It's decreasing from negative infinity to 0. It's decreasing, and then it increases here, and then it decreases on that last part. Make sense? Now notice we said it concaved up at 0, negative 2, and it concaved down over here at 2, 2. Now, here's the deal though. The true concavity, where it concaves up, is actually from negative infinity to the point of inflection, which is 1. Because as soon as it hits this 1, it starts concaving down. So, concave down actually at 1 to positive infinity. So the concavity is actually these two intervals. This is the point of inflection where the switch happens. The concave up and down switches right here. So negative infinity to 1 is concaving up. It hits this point, and that's where the concave down starts to occur. Cool? Okay, so this was a really good example. It actually took everything to account that we have learned so far. My recommendation is you rewind this particular problem so you can see how we started it and why we did what we did. Now stay tuned. I got a story for us. Okay, so we just read a story, but let's kind of go over it. It says a person coughs when a foreign object is in the windpipe. Well, that makes sense, right? The velocity of the cough depends on the size of the object. Suppose a person has a windpipe with a 14 millimeter radius. If a foreign object has a radius r, which is in millimeters, then the velocity, which is in millimeters per second, needed to remove the object by a cough is given by this particular function, where k is some positive constant. So I don't know k, all I know is it's a positive number. For what size of the object is the maximum velocity needed to remove the object? Okay, so I need to make myself a note. K is a positive constant. Right? It's positive. Now, their question was, what's the maximum velocity needed to remove the object? Well, when they say maximum velocity, they're actually asking us to find a relative max. So to find the relative max, here we go, just like we've been doing. First things first, find that first derivative, which will help me find my critical values, correct? Now here's the thing, I'm finding the derivative with respect to r. K is a constant. It's a positive, it's just a constant, it's just a number. I could distribute it through, but I'm not going to waste my time and do that. If you want to do that, be my guest. But it's just a number, and it's going to get multiplied by the derivative of those parentheses, because that has the r in it that I am working with. Cool? So to find the critical values, that's right, set this equal to 0. And yeah, this is a multiplication problem, so I'm not going to worry about the k, all right, because it's just a number. So I have a number equaling 0. That doesn't, I mean, you could do this, but that's not necessarily true. This is some number. So this one is out of the picture, so to speak. And now I'm going to work with 28r minus 3r squared equaling 0. Let's factor out that r so we can solve this. So one of our r's is 0 and the other one is 28 over 3, isn't it? Good. Now normally we would plug this back in and find the y's, correct? Or the v of r in this case. But because I don't know k, I can't find the y value, so to speak, that goes with each of these r's. So that's a step I'm going to end up skipping. So I kind of skipped step 2, where we find the y's. And I'm going to go straight to step 3, which is to find my relative extrema. Now, you can do the first derivative test, right? Which means you're going to find where it increases and decreases, and that'll tell you the relative min or max. But I'm going to choose to do the second derivative test. Why? Because I find it very easy. Because all I have to do is take the second derivative of this thing, and I can do that pretty quick and not worry about having to graph. Again, k is just a number. I don't really know what it is, and it doesn't really matter at this point. Good with that? Okay. And now I have two values for r. I am going to plug them in so I can see what might be my relative min or max. So what do we get here? We just get 28k. Now remember, k is a positive number. That means this is greater than 0, isn't it? So if it's greater than 0, which way does it concave? Yeah, greater than 0 means it concaves up. That's not a relative max, that's a relative min. So this isn't going to do it for us, right? The second critical value we had was at 28/3. So when we plug it in, 28 minus 6 times the 28 over 3, right? Okay, let's do our algebra, 28 minus the 56, what is that, negative 28k? Again, k is positive, so I have a negative times a positive, which is a negative. So what does that mean? It concaves down. Good. That's my relative max. This is what I'm looking for. So the size of the object, as it's asking, the object actually has a radius of what? Yeah, 28 over 3. What is its units? Millimeters. Or we could say 9 1/3 millimeters. Cool? Lovely. Okay, you guys have fun with this stuff. I'll catch you on the flip side.